Welcome to Lecture 7. Today we will be covering Newton's laws of motion. So Newton has three laws of motion. He was a English physicist living in the 17th century, and today his three laws of motion are some of the foundations of what we call classical physics. So here are the statements of his laws. Newton's first law states that an object will remain at rest or in uniform motion in a straight line unless acted upon by an external force. His second law states that the net force on an object is equal to the object's mass times its acceleration, or that F equal ma, where F is a vector and a is also a vector. And his third law states that if an object A exerts a force on an object B exerts a force of equal magnitude and opposite direction on object A. So we will go more into what each of these individual laws means one at a time, but first I want to go over some limitations of Newton's laws. So Newton's laws don't apply to very fast objects. That's the domain of relativity, special and general relativity developed by Albert Einstein in the 20th century. And what happens in relativity is that as objects go faster, you realize that space is not three dimensions of space and one separate dimension of time, but rather four dimensions of space-time. And that changes the ways in which objects move and behave in ways that cannot be predicted by Newton's laws. And Newton's laws also don't apply to very small objects. That's the domain of quantum mechanics. And basically, what we can create with Newton's laws is what we have as Newtonian mechanics, which are the description of kind of the very basic motions of objects, forces, rotations, things like that, using in a formulation based on the quantity of force. There are other formulations of classical mechanics, the Lagrangian and Hamiltonian, for example, but Newtonian is kind of the easiest to comprehend when you're starting off, and it's the one based on force. And Newton's laws also form the cornerstone of classical physics in general, which is physics without relativity and without quantum mechanics. And where Newton's laws do work is in the everyday world. You know, if you have a car going at 1,000 miles an hour, which I hope you don't, then that's not very fast at all. In terms of the speed of light, which, if I remember correctly, is like 100,000 miles per second or something. It's not very fast at all, and so it's very clearly the domain of Newtonian mechanics, and of course, a car is not very small at all, so there isn't much quantum randomness going on. So Newtonian mechanics may not be a perfect description of what happens in reality, and really, I don't think either relativity or quantum mechanics can claim to be that, but it works very well for kind of the everyday situation, and that was really the situation that physics was looking at until right up to the 20th century with relativity and quantum mechanics. So when we learn introductory physics, we learn this because it is what applies to the world that is most accessible to us. So let's talk a bit more about Newton's first law, which stated that an object stays at rest or in uniform straight line motion unless it is disturbed. So this gives us kind of the concept of inertia, which is that an object has its own motion that is affected only by a force. So we'll hear more about this with momentum and kinetic energy. But basically, we can think of inertia as an object has some sort of motion with it that is affected by a force. And again, we will talk more about this when we reach momentum. And also the way that the first law is formulated kind of implies Galilean relativity, if you remember what that is. I believe we covered it in lecture 1 or 2. But basically, notice that we're saying that at rest and traveling at a constant velocity in a straight line are basically the same thing. That is the statement of Galilean relativity, that you can interchange between inertial frames with only a change in velocity. And I say inertial frame here, and this is going back to, I believe we said this on the previous slide. Okay, I did not, but basically, this law only applies to inertial frames, because in non-inertial frames, where the frame itself is accelerating, you have the issue that an object that has no external force on it is accelerating along with the frame, so it's not actually at rest or in uniform motion. So that's why that doesn't work. But if being at rest or being at uniform motion are kind of two sides of the same coin, then it does imply Galilean relativity. And of course, we have the idea of zero net force, where two forces cancel out. If I push on my water bottle from the left and from the right with equal strength, it doesn't move, but there it is sliding when I only push on it from the right. If two forces balance out, that's the same as if there's no force at all. And now Newton's second law. Again, we have to fix this in non-inertial frames, because in non-inertial frames we get what are called fictitious forces caused by the frame accelerating or rotating or what have you. And we may not cover this in the course, but it is important to keep in mind that Newton's first and second laws really only make sense in the context of an inertial frame, which is a frame that is not accelerating and is instead only at rest or moving at constant velocity. So force is a vector that is measured in newtons. We already went over this, but it's important to understand the idea of force and acceleration being parallel vectors. Force is a scalar multiple of acceleration. That means that they're parallel, they have the same direction, and their magnitudes are just scaled up or down by the kind of conversion coefficient of mass. And it's also important to realize that the same force on two different objects will give two different accelerations. Like if I push on my water bottle, for example, it'll move. It might not move very fast, but it'll move. Whereas if I go outside and I push on a garbage truck, say, that garbage truck is not going to move nearly as fast. And even if we're neglecting friction, the fact is that because S equals ma, if m is higher, a will be lower, and vice versa. And this will be important to remember when we keep in mind the third law. So Newton's third law may be a bit difficult to comprehend at first, but basically there are no unpaired forces. Every action has a reaction. So a good thing that we can realize using the third law is that a system of objects cannot move itself. Let's assume that the third law is wrong, right? And let's say we have two blocks. If one block somehow reaches out and pushes the other, and the other block doesn't push back, then that means that the system is all of a sudden going to start moving to whichever direction the first block was pushing in. And that is something we cannot have without the system acting on something external. Instead, what happens is that the other block pushes back with the same amount of force, but in the opposite direction. So the two blocks just kind of fly apart from each other, but the center of the system stays the same. And it's important to realize kind of what a system is. A system of objects is it's a group of objects that they can exert internal forces on themselves, but basically we consider them one unit. And the system of objects can have a center, we can call it the center of mass, and we'll discuss all this later, but the system cannot move by itself because of the third law. And let's switch context between these two blocks in the system, and let's talk about, say, you and the Earth. So you may be thinking, okay, the Earth is pulling down on me with gravity, right? So why am I not pulling up on the Earth? Like I can feel myself being pulled down, but I can't see the Earth being pulled up. Like when I walk, why don't I pull the Earth? Or if I jump, why doesn't the Earth come up to meet me? And as I'm saying this, I'm realizing that these are fairly silly sounding questions, but it's important to realize that because of F equals ma, you guys, you and the Earth may exert, well, you do exert the same force on each other, but you don't accelerate nearly as fast. I mean, the Earth does not accelerate nearly as fast as you do. So, because the Earth is, so much more massive than you are, it doesn't accelerate. And it's also in how you think of it relatively. If I am considering myself to be a frame, and I jump up, and I'm always considering myself to be the origin of my frame, then I do indeed see the Earth jump up to meet me. However weird that may seem to those of us who are not used to pretending that we are at the origins of our own little frames. That is a quick introduction to Newton's laws. These are all powerful things. if you have a system, then remember to take into account your third law conjugates and use F equals ma to find the acceleration of your objects. And yeah, basically these three laws just kind of lay the foundation for Newtonian mechanics and physical thinking as we knew it for the longest time. So yeah, thank you for watching this lecture. Please email me if you have any questions or want to meet up so we can clarify some concepts.